only thing that is the electronic stuff that we did before. The other, yeah, the other stuff is a little bit more involved, and we've burned through so many components that there's not a ton of stuff left. Right, terminal voltage. So the terminal voltage is found through EMF minus the current times the little r here, and little r here is the, where is it? That guy, the internal resistance of the battery. So you get something that looks like this. Instead of drawing it like we used to, we now draw them like this. We put a dotted, that's really blurry and kind of gross. There we go. Come on, figure yourself out. The dotted line around here, shaped like a battery. We've got the internal voltage and the resistance there. So we did one example yesterday. If a 12-volt battery, like a car battery, for example, has an internal resistance of 0.22 ohms, what's the terminal voltage of the battery when a current of 3 amps flows through the battery? So that's just a VT equals epsilon minus I times R. We found that the voltage from the battery, the thing it's actually supplying, is 11.34 volts, since it has a current going through it. And the larger the relationship here, the larger current you draw, the more voltage you're going to lose from the EMF. This actually works in reverse too. When you have a rechargeable battery, when a rechargeable battery is being charged, an external voltage is applied to the battery. Basically what you're doing is you put the batteries into a charger, you put them in backwards, and then you plug the thing into the wall. The large voltage difference in the wall, 120 volts across a plug, your little batteries, your 1.5 volt batteries, their voltage cannot compete with what's coming out of the wall. So that large potential difference in the wall forces the chemical reaction backwards in these rechargeable batteries, resetting it to almost what it was to start, and that's how you get a rechargeable battery. So this is basically what it says here. In order to force electrons backwards in the battery, the external voltage must be, where is it here, larger than the EMF. And so there's a bunch of ways this happens. For your little AA, AAA rechargeable batteries or your computer battery, all of these things are getting plugged into the wall because the wall provides 120 volts. I don't know what a computer battery is, but your standard AA's, AAA's, 9-volt batteries are 1.5 to 9 volts. Your car battery is a 12-volt battery. So the alternator in your car is going to have to be providing a larger voltage than the 12 volts the battery is supplying to make sure that your car battery stays charged. The external voltage is actually going to have to be at least this VT, we're going to call it VT external, is going to have to equal the EMF now plus I times little r. And this right here, we add the EMF to the internal voltage drop, the current times the internal resistance. We add them together only for charging, or only when charging. So on your formula sheet, how you're actually going to see it when we write these things down, and typically how we quote terminal voltage is we just write it like this. VT is equal to epsilon plus or minus IR, and it's understood that the plus is for charging, the minus is for draining, when you're actually using the battery, or whatever it is. So the example we have here is this. A 12-volt car battery is being charged by an alternator that can supply 15 volts. If the internal resistance of the battery is 1.3 ohms, what is the current that's traveling back through the battery. So because we're told that this thing is charging, we're going to use our epsilon plus IR, or EMF plus the internal voltage drop. So we've got VT is equal to 8 plus I times R. The 12-volt battery, that's the EMF. The 15 volts, that's what's being forced across the terminal by the external alternator. We know what the internal resistance is, and so we can run this through to find the current through the battery. So 15 is going to equal 12 plus I times R. No, we know what R is. What did I say? R is 1.3. So 3 equals 1.3 I. So what's the current through that battery? Good morning, sir. 2.3 amps. That's it. So this is the concept known as electromotive force. Do I do another example for us here? You know what? I think I'm going to leave it there. I'll let you play with this stuff. We'll flip the page here. I left you a blank page there. There's a few things that I thought about writing down, or examples I thought about giving you, but I think you'll be okay without them. So the rest of this is just EMF practice. We could have finished that lesson yesterday had I not been talking with students to start the class. So that's EMF, and that's as far as we're going to take circuits at this point. So you've got the answers to these questions. I want you to do them all. And then, what's today, Wednesday? We'll say Monday. Monday is A, B, C, D. Students, we have class right after lunch. Monday is going to be your circuits test. So I've got, sorry, Monday is your circuit test. Today's Wednesday, we got 2 short blocks, and we're done circuits. This is it. So what I've done here is I've included a circuits review assignment for you. This is not something you're going to hand in. The very back, I've got the answer key here for you. I've got lots of these reviews. I have 2 more of these things for circuits if you need some more. And because this comes straight from what used to be part of Physics 12, this is just what I use for them. So take a look at the EMF practice, and then I want you to start launching into the review assignment here on circuits. That's what we're going to do today. There's my lesson done. There you go.